to you.
Thank you. So this is the best session of the entire conference, of course. Glad you stayed this long. Yeah, when Matthias and I spoke about the scheduling and he said, well, I'll put you on the last slot and the last day, I go like, okay. But anyway, I'll do some juggling and stuff to entertain you. No. We'll talk about Java and the Internet of Things. We've heard a lot about the Internet of Things, smart devices proliferating everywhere. And I'd like to dive in a little bit deeper into some of the technology, some of the problems that we're facing in building these systems, and also show some demos on one of the products that Oracle is working on and has released. So my name is Terence Barr. I'm a product manager for Oracle Small Embedded Java products. And yeah, I'll just go right into it. So this is the agenda. We have plenty of time, so I hope to make this interactive. If you have any questions, just interrupt me and we'll discuss it. So we heard this topic before, sort of the third IT revolution, but I'd like to go a little bit deeper into what it actually means for us as software developers and what the opportunities are. And I actually mean opportunities in the true sense of the word, because I believe this is actually, the best is yet to come for Java. There's going to be a huge demand for software engineers building these smart distributed systems, permeating every part of everyday life. And this is a big opportunity for Java developers. If you've done Java, if you're familiar with the paradigms, with the language, with the programming model, with the tools, the idea is to make it really easy for you to move to embedded, rather than learning a whole new skill set and taking years to develop the skills and learn the languages and the tools. You should be able to very quickly move to embedded and start building solutions and make a career and make some money out of that. So that's the opportunity. We'll talk about, of course, Java we think is the best platform for the Internet of Things. And then I'll go into the actual product, Oracle Java Me Embedded 3.2, sorry. 3.3 is coming soon. Talk about some of the APIs, some of the features. Then I'll do a demo. I actually have two demos. I have one sort of full-blown demo from an industrial control use space, and then I'll also try to do a quick, how to develop an app and run it on the system. And then an outlook on what's coming in the near future for embedded Java. And again, questions if we have any. All right, so I don't know if you can guess what this is. You saw the picture before? So this is not a galaxy or something out in space. This is actually a visualization of a small part of the internet in 2003 where they show the nodes and the routes between the nodes. And I thought it was just interesting because it visualized, this is a small part of the internet 10 years ago. You can imagine what it would look like today. There's just this explosion of devices and data traffic that's happening. So, in the 90s, before that, we had sort of the one-to-N relationship where there was one computer and many people using it, the age of mainframes, and then slowly we, went to personal computers. Basically now we have 10, 12 billion devices connected, mostly still sort of a 1-to-1 ratio, maybe a 1-to-2 ratio, right? You might have a phone, you might have a laptop or a tablet, but still the numbers sort of mostly driven by the population on the planet, right? But with devices getting smarter, we're going far beyond that 1-to-1 ratio where you might have 1 or even 100 devices around you doing things, right? So that's the Internet of Things. The numbers range anywhere from 20 billion to many trillion, depending on who you ask. But I think by any measure, it's going to be a very large number. So what is driving this? There are a couple of factors that are coming together. One is just the fact that hardware is getting cheaper and more capable and requires less power. Connectivity is a major part of this. So it used to be that when you built an embedded system, it was sitting out there and was disconnected and didn't really interact with anything. That's changing. Things are pretty much connected by default, by design. Might not always be connected, not permanently connected, but they have some way of connecting. And then there's a value shift, and I think we've seen that in the industry in general, right? From the hardware drives the functionality to the hardware is becoming a commodity, and the functionality, the upstack value is actually in the software, right? That's why our profession as software engineers is getting more and more valuable, because most of the value is generated in the software, not in the hardware. And then generally a movement in the entire industry, you know, towards the trend of being faster to market, reducing cost, being able to scale, to build on commodity parts, and generate solutions that are long-lived rather than single-point solutions. So if you look at, and I think Henrik had this slide yesterday in the opening keynote, you know, if you just take a quick picture of what's happening today, you're seeing people connecting all sorts of devices in all sorts of verticals for different use cases. And this is just sort of a cross-section. And we're really barely getting started. Most devices today are fairly dumb. They don't do a whole lot. You know, smart meters, as we heard, are not really that smart. And we're just sort of on the cusp of this. Now, if you look at, there's a lot of complexity behind this, right? Just connecting devices is just a very small part of the problem. If you look at one use case like smart home, for example, you can see that things become more difficult because you have multiple devices that are potentially tiered, right? You have devices that have a dedicated functionality, don't do much, might only have short-range communication. They talk to a gateway. The gateway is more capable, does routing, does protocol translation, talks to a backend. And then the data and the control flows into different domains, right? So you could have the utilities company wanting to access and read some of the devices in your home. You could have the appliance company, the security company. So you have different domains, right? And of course now security, management, monitoring, all of that plays a big role. So this is just a snapshot on some of the complexities. So if we take a step back, you know, why is Internet of Things, or you know, why is small embedded development different? And I think at a high level, you know, it really boils down to these bullet points. First of all, you have, it's very different from the PC space. You don't have a dominant architecture, dominant operating system. The number of devices and the permutations of hardware and software combinations is just staggering. Because these devices potentially sense and process sensitive data, you have to absolutely take care of security, reliability, privacy issues. These devices sit out in the field and potentially are very remote. There's no human interaction, and you don't want to ever get into the situation where you have to send a technician out somewhere to fix one of these devices. That probably breaks your business model, right? Because you don't have that buffer in cost to allow you to do that. The devices might sit out in the field for a long time, for a long number of years. So you have to be able to not only monitor and manage them, but also upgrade them while they're in the field. So let's say you have a smart meter, and the smart meter, you know, does some local processing and then sends the data off to the utilities company. Well, if the regulatory environment changes, if the law change, and the way that data is being processed changes, and you need to adapt the algorithm by which your smart meter works, well, you can't afford to send someone there, you know, every 5 years or something and update millions of smart meters with a new algorithm, right? So you have to be able to upgrade them over time, add functionality, increase the value of these devices. Connectivity is a big topic. It's not as easy as just plugging in Ethernet or Wi-Fi and having an IP address. Some of these devices are very low cost, power sensitive. They might not even have IP connectivity. They might sit on some short range radio network. with a router in between to route it to an IP-based network. BOM cost of the device is always a problem. And then really it's all about the data. At the end of the day, why are you doing this? It's about the data that you generate to improve your processes or to even enable new business models, right? So you have to think about the flow. How does the data get from the device all the way to the back end? And how can the back end push new data all the way down to the device to change its behavior? And there's one thing that's really important to realize is information and data are not the same thing here. Data is just, data, just values that, depending on the circumstance, might not actually mean very much to you. You want to turn data into information. So to give you an example, if I'm monitoring a shipping container, for example, and that shipping container, I need to keep the temperature within a certain range. I don't care that the device monitors the temperature and then sends a temperature reading every 10 seconds to a backend. That's meaningless data to me. I don't even know what the context is, right? What is the temperature range? And it generates a lot of traffic as well. So what I want to do is, and this is really key, I need local intelligence on the device. I need to have a business logic and a programming model that allows me, for example, to filter the information and filter the data and turn it into information that's meaningful. So, for example, I only send an alert if the temperature is outside of a given range. Yes? Sure.
So what if this business model changes? Because you said that you cannot afford changing this very often, right? So I think that I see conflict here. Because if you want to move this logic to the device, on the other hand, you want people to change this without having to manually go and update it and configure the device, right? So
okay, so the question is, what if the business model or the logic changes? Actually, I think you misunderstood me. What I said earlier was you want to be able to change the logic and you want to be able to update the way the device behaves easily, right? That's exactly the point of a smart device, of a device that's upgradable. So you can easily push down new business logic over time. You do not have to send somebody there to change it, to upgrade the software, right? That's the whole idea. By having that flexibility and being able to push upgrades into the field in a secure, reliable manner, you can add value and make your service and your device much more valuable over time, right? And then finally, this is something that concerns us. Developer productivity, development reuse of code, of existing skills. That's what I said before. There are, by some estimates, only 200,000 embedded developers in the world that can do deeply embedded development. And that's a very specialized skill, and those people specialize in certain platforms and technologies. We're never going to get the growth in the ecosystem and in the industry if we have to rely on a couple of thousand people with specialized skills to build stuff that takes years, to implement. That's not how we get to scalability. We need to have a programming model and an environment that makes it very easy for people to take their skills and deliver solutions quickly. So really, if you take a step back, there's a common theme here, and the theme is if you look at the smartphone market, for example, the mobile phone market in general, right? So many years ago, before the appearance of software platforms in the phone space, or even take the early PC space, right? There was this proliferation, this fragmentation of all these different operating systems and hardware and software tools, and it inhibited the growth for everyone, right? Because you basically had to reinvent the wheel every time you built a product. And the embedded space is in exactly that position today. It's a very fragmented space, and everybody reinvents the wheel and the plumbing every time they build a solution. So what we need to do in order to enable this ecosystem to take off is to move from a proprietary single point approach to a horizontal platform approach that's scalable, right? Where you have common functionality that you can build upon. So all these different verticals and industries have very similar needs. They need an application platform, they need security, they need connectivity, they need manageability, they need interoperability, backend integration, all these nice things. You always pretty much need the same set of features, right? So that's really the core value behind this, building a horizontal platform that allows you to build on top so you don't have to reinvent that plumbing every time. So naturally, we like to think that Java is the best platform to do this, and I think there's some good data points. So if you take a step back even further, and this is Oracle's vision for the device to data center approach. If you take a step back and you look at the entire solution, right, it's not just about, you know, what device do I use and what programming language do I use and how to connect, right? It's much more about building a solution where the data and the value flows from the device, from the edge, all the way to your back-end systems where you do something useful, you improve your business processes, you deliver some service and value, and then some of the data flows back to impact how the devices operate, right, to optimize things. And you have multiple tiers. So at the far left, you have the actual devices. Those might connect via short-range technology into a gateway. They might, if they're more remote, connect directly to a cell tower, for example. There is some technology involved in the wireless transmission, the cell towers, the billing, the switching and so on of the data. And then you go into this service enablement tier, which is here in the middle, where you start processing the data, you do some analytics on it, you do some event processing. For example, you can find out, well, if I have millions of devices sitting out on the edge and the data keeps streaming in, by analyzing data in big blocks from multiple sets of devices, I might be able to deduct and infer certain conditions that are out in the network. So for example, failures of a set of devices, right? I can do that with event processing. I can start overlaying that data with other data, for example, spatial data to create some more value out of the data. And then finally, at some point, the data will actually flow into a backend either for storage or for further processing in a CRM system or in an industry-specific environment, say, retail or logistics or something, right? So if you look at this whole device to data center, and again, you see in the red bar, right, there's a common thread of functionality that you need to enable this. That's the horizontal platform. And so when you're talking about the Internet of Things, this is something you really have to keep in mind is what is the end solution that I'm actually trying to achieve. It's not about what specific technology I'm using on the device. That's actually fairly minor. And Java really plays in all of these tiers. Java is already present on about 10 billion devices in the world. Of course, we all know Java is one of the, if not the most widely used platform in the enterprise. But it's also present on many, many embedded devices that you wouldn't necessarily think of, right? Like Amazon Kindle and Blu-ray players and things like that. And so Java is really the single development platform that spans all these different domains. And that's really where the key value is, because it allows you as a developer to approach this problem with a common mindset. You don't have to segment the problem into different tiers with different tools and different programming models and different architectures. You can take in a whole vision, a holistic vision of the solution, and leverage Java benefits like portability and security and interoperability. And all these features that we've come to love with Java, that in the embedded space, those people are still struggling with moving from 8 to 16-bit architectures or from single-core to multi-core CPUs. That's a huge problem for them. And Java solved this problem a long time ago. And so that's a quantum leap for embedded development. So let's dive down a little bit more that was the high-level view into the client technology. So, you know, when I talk to embedded developers, there's often this notion of, oh, you know, Java's big and Java's slow and it won't fit on my device, and, you know, I need to fiddle with every bit and write really tight loops. And that might be the case for some solutions, but I believe what we are seeing is that 80 or 90% of the embedded use cases don't have those requirements. They allow you to add more intelligence on the software platform and make your life easier in many ways. So if you do sort of a simplistic comparison between Java and native, right? Of course, the first benefit is it's cross-platform, obviously, right? You don't have to cross-compile. You take your code and you just run the JAD and the jar file on your other device. You don't have to cross-compile like in native. Really, really important is security. Getting security right is a very difficult process that takes a lot of time and expertise, and Java's already solved that problem, right? We have a sandbox model, we have virtual execution, we all know that. Again, this is all, you know, new to embedded developers. It's very robust. It's very easy to make pointer mistakes in native and the system crashes and burns, right? Multi-threading, of course, we take for granted. It just works. Performance, that's one thing that people, you know, always complain about. And in fact, it's funny, I don't know if somebody read Jasper Pott's blog a couple weeks ago when the JDK for the Raspberry Pi was released, the early access version with the hard float support. And Jasper Potts did some testing, and he ran some number crunching algorithm, I forgot what it was. Fairly simplistic benchmark, but still, you know, relevant. And he compiled that with some optimizing version of GCC. So he had the C-based version, and he ran that against the Java version with some tuned hotspot settings. But it was, you know, the standard JVM. And it turns out that the Java version executed faster than the optimized C version. So, of course, that's not always representative. But, you know, the notion that Java is big and slow is outdated, and I'll show you in terms of size how low Java can actually go. Where Java, of course, really wins out is on the development model, obviously. I mean, you can be, you know, X times more efficient developing Java than you can be with native code. And you can reuse a lot of this. I mean, that's one of the beauties of Java, right? If you have an algorithm, you have a problem you want to solve, there's almost always somebody who has already built a library to do exactly what you need, right? And you just drop that into your project and off you go. So let's go down a little bit deeper. If you're talking specifically, you know, what are the kinds of things you need to build these smart systems? As I said, they have to be robust and secure. They have to be available and functional for a long time. And increasingly, you need more and more features. You know, in the past, it used to be that embedded devices were single purpose. They did one thing. It was very simple. You know, you had a little bit of code. That's all they ever did. Now, increasingly, you know, people expect more features of these devices. And it's now doing something like that in native becomes very tricky because you have to integrate different libraries, right? You have to write a bunch of code. You have to take care of the security, of connectivity. You have to do a lot of things to make that work. And in Java, you have all that out of the box. We spoke about local intelligence. That's very important to be able to make local decisions that allow you to create more functional solutions and products. And hard and software independence, I think that's another one that's underestimated. People say, oh, you know, I just quickly recompile, you know, from my ARM architecture to my PowerPC architecture. Just quickly recompile my native code and I'm done. Well, to give you an example, we're working with Électricité de France, which is the French utilities provider, and they have a government mandate to implement smart metering across the country in France. And because of the government regulations, they also needed to have a multi-source strategy for their hardware, for the smart meters. So they had to be able to take the hardware products or the hardware smart meters from multiple different vendors. And of course, what you don't want to have is support multiple versions of the code that's running on those smart meters just because you have to multi-source from different vendors, right? And even worse, over time, you might update hardware. So you might have different versions of the hardware in field at any time, right? So over 10 years and millions of deployments, you might have 20 different versions of hardware sitting out there, and you all have to support them, right? You have to create multiple versions of the same app. You have to do all the testing, all the qualifications over and over and over again, right? It's not scalable. So they chose Java, and they said, okay, all we need to do is, if we get a new version of the hardware, we port and we test the VM once, and then we can deploy it. We don't have to redevelop and retest and requalify the application because we've done that work on the VM, right? Very, very important. Was there a question back there? Did you raise your hand? No. Okay. So, yeah.
But this is given that all of those hardware support Java, right? I mean, all of those vendors, they should support Java, right?
Right.
So that could be a limitation as well, right?
So the question is, that requires all those vendors to support Java. Yes, well, the way you would do that is that as part of the sourcing agreement with the vendor, you just say, well, you have to have Java, right? That's part of the bill of materials. And then they would go to a third party and have them implement Java. So it just becomes a requirement.
Just to add on to that question, I mean, the same goes with the power awareness, right? That will also depend on how much the hardware provider is actually exposed to the virtual machine in terms of power awareness.
Power awareness and power management, right, exactly. So, and again, one of the difficulties for embedded developers is you might have a particular hardware that is very power efficient, and you have to interact with the power management system in some way, right? And you have to have dedicated code to do that, right? And then you move to a different hardware architecture which has a very different power management system, and you have to rewrite all your code again, right? With the Java stack, we have one API that's common across all hardware architectures that allows the application to interact with the power management system in a defined way. And so your application just ports from one platform to another without you having to mess with the underlying specifics of the power hardware management. Okay, so going still deeper, we'll start talking about the actual product in a minute. Just to give you an overview, so Oracle released two products in September of last year, dedicated to this space. So one is Oracle Java Me Embedded 3.2. That's the product I'm responsible for, and that I'll talk about the rest of the talk. So that's more for the edge devices. And then there's Java Embedded Suite 7, which is more of a gateway type product. So that is a complete Java SE runtime with JavaDB and a Glassfish application server instance on top. So that is more geared towards the more powerful embedded devices that sit in the middle tier and handle traffic coming from the embedded devices on the edge. And then that, of course, can go into the back end for further processing. So just to make sure you have that separation in your head. So let's talk about the product itself. So what is the space that we're targeting? We're really going from fairly low embedded, around roughly 256 kilobytes of RAM, somewhere up to 10, 32, maybe even 64 megabytes of RAM. So it's a pretty broad range. Above that, you would probably want to use a Java SE embedded system. Those typically start around 32 or 48 megabytes of RAM for the more powerful systems, right? That's Java SE embedded is used in high-end systems like, high-end medical devices like radiology systems, ATM machines, high-end copiers, and things like that. But pretty much everything else is covered with Java ME, right? So ME, of course, being micro edition, Java SE being standard edition. Except for the very low end, that's Java Card. That's a really dedicated special purpose Java runtime for smart cards. It has a lot of special features. And that's a specialized market that we're not really targeting. We're targeting a broad range of sort of horizontal devices. And we're also going after a broad range of architectures in terms of processors. So starting at the low end Cortex, ARM Cortex-M microprocessors, and going up to MIPS and even PowerPC. Not yet, but that's sort of in the planning. Right, so what is Oracle Java Me Embedded? It's a high-performance Java runtime specially dedicated to the small embedded devices. It's a complete runtime, so it contains everything you need. You don't really need to add any integration work. This is different from, as I said, Java has played a big role in embedded in the past, but they were very often specialized products and deployments. So, like Blu-ray players or medical devices, or in-flight entertainment systems in the Airbus and so on. What we're doing here is providing a horizontal platform that's readily usable for embedded developers. We've added a couple of dedicated APIs and features for the embedded space, and I'll talk about those some more. The product is actually based on. The reason the version number is 3.2 is it's actually the first sort of dedicated embedded release, but it's built on Oracle's feature phone Java runtime that's been around for many years. That's shipped hundreds of millions of devices. So it's a very mature, robust technology. And we've actually tuned it in different ways to make it work even better on small embedded devices. And then it comes with a complete tool chain. So I don't know if anybody has used the Java ME SDK before. So we updated the Java ME SDK to now support embedded development as well. And if we have time, I will show you a demo. So what are the types of devices we're targeting with the first release? So right now we're targeting mostly the ARM space, the smaller ARM processors, ARM 9, ARM 11, ARM Cortex-M. We can easily support Cortex-R and Cortex-A as well if there's a requirement. So we're looking at resource-constrained devices that are always on, that don't have graphics, right? So that's really the bulk of the market. You can cover a very broad range of use cases with these requirements. We don't really need much of an operating system, right? So many people say, oh, does this run Linux? Do you need Linux? No, Linux would be much too big for these devices. We're talking about several hundred kilobytes of RAM or maybe a megabyte or two of RAM. So we only need a very simple OS, maybe a real-time OS, a small kernel. Everything else is done at the VM level, things like threading, resource management. Even some of the device drivers you can write in Java. Connectivity, we're very flexible, right? Connectivity is important. We do IP-based connectivity at this point, either wired or wireless. And you can actually also, the application, in these embedded devices, it's very important for the application to be able to choose its connectivity wisely, right? So you might have a device that sits out in the field that has multiple ways of connecting to a backend. Some may be slower, more expensive, some may be faster, but not always available. And so the application, there's an API for the application to actually get notified when certain connectivity options become available, and then can switch its data transmissions and optimize its data usage based on that, right? So, for example, you could say if I only have a slow, expensive connection, I'm going to cache a lot of the data, and I will only send things that are absolutely critical. And then later, when my other option becomes available, I'll send the bulk of the data, right? So again, the need for local intelligence, right? You can build better products if you have a local way of processing data and executing algorithms. Peripheral I/O, it's important that Java applications can interact with devices. So we have an API that allows you to interact with a number of different types of I/O, and I'll go into that in more detail. without writing any native code, and this is cross-platform, right? So you can take your application and go from an ARM-based system to a, I don't know what, PowerPC or a MIPS-based system, and you don't have to recompile it, and it'll just work. Assuming that the devices are similar and there are native drivers for the devices. But at a Java application level, you don't have to mess with the specifics of the system. So now to talk about the footprint in particular, so if you want to make it really, really small and you're willing to shave off some features, we can go as low as about 130 kilobytes of RAM and about, 350 kilobytes of ROM. Yes?
Are you going to shave even more? Because I have lots of devices with like 16K ROM that would, it's kind of far from that still. So
right.
Would it be possible to shave just
more?
So
can you make it even smaller? So yes, we've spent a lot of time thinking about that. There's a vast market for really small microcontroller type devices. They often have 32K or 64K of RAM. And of course, the volume is very high, right? You produce billions of those. However, that's so small that you have to start shaving off so many features of Java that you lose some of the key benefits of Java, right? So once you don't have certain APIs, and once you're not able to update Java classes on the fly, and once you have to make all these compromises, at some point you lose the value of Java, and it's really, it's just write a little bit of native code and be done, right? There's a trade-off in putting a lot of effort and engineering into making Java really small, and then you face a very dedicated business model and use case, and it's not clear that Java really has an advantage there. And I don't think that's the market we want to go after, honestly, right? Because that's been served pretty well in the past with existing methods, because the software stack is pretty small. Things are fairly straightforward. It becomes much more interesting once you have more software functionality. These things become more intelligent. That's where Java really provides a value, right? So there's a huge horizontal sort of play here that is not addressed today, and that's really what we're going after.
Yeah, but I think it's there will be plenty of really, really small devices doing this, measuring temperatures and all sorts of things. And I think it's going to be lots and lots of developers doing nice stuff with this. I think the flash size is right, but the ROM size, if we could go down just a bit more.
So there will be lots of devices doing measurements and things, and that's true. Typically what you do in that case is you have a tiered solution, right? So you have a small little microcontroller that does some measurements, and that basically doesn't do much and just passes on the data to a system that processes it. Right now, if you look at the evolution of system-on-a-chip system, SoCs, from ARM and other manufacturers, having 256 kilobytes of RAM and 2 megabytes of ROM on chip is going to happen this year. In 2013, these will become available. And that is a very comfortable platform for this Java stack. 256K of RAM, 2 megabyte of ROM. You can do a lot of things there. And so you can build pretty small, fairly cheap devices with no external memory that can fill a lot of these use cases. And again, going smaller might not be worth it, from a Java perspective. But I think there's plenty of opportunity with what we can cover here already. All right. So some more features. So even though this VM is very small and compact, we have a lot of good features in there. We have a fully multitasking VM, so you can run multiple applications at a time. And they're isolated from each other. So if one application misbehaves, then it won't pull down the rest of the system. And in fact, you have a complete application management system, which allows you to remotely start and stop and kill applications, install, update applications. You can do all that. It's been tuned for low footprint and efficiency. We've optimized the garbage collection. You can configure the VM remotely, or at least some aspects of it. You can drive the entire runtime completely headless, so you can have something sitting out in the field with no display, no user interaction, and fully operated. It's portable and extensible. It has a number of features. It allows you to, for example, automatically recover from errors. So if one application terminates for some reason, it can automatically be restarted, or the entire system can be restarted. Yeah, we spoke about the footprint requirements. So what are the types of use cases that we envision this going into? And this comes back to your question to some extent. So we're really targeting the use cases where you need a little bit more horsepower, you're doing a little bit more local processing, you need a little bit more local intelligence, but that's a wide range of use cases, right? So things like wireless modules, and I'll talk about some of the partners we're working with. I have an industrial control demo. It's being used in smart sensors. There are applications for e-health, and then just a general, as a general application platform for Internet of Things type applications. And we don't really see, we see this as a singular solution. We don't see anything really that competes in this type of environment and breadth. There's nothing really that offers similar functionality. So the tool chain I spoke about, that's very important for embedded developers. And if you're familiar with Java, you've done development on Eclipse or NetBeans, this will be extremely familiar because we have plugins, and I'll show you that in the demo. So basically, it looks just like any other Java platform, only you choose the platform beforehand, right? So you choose basically the set of APIs and features that you have, but you stay within NetBeans and Eclipse, and you just write your code, you compile it, you download it or provision it to the device, and off you go. And we have an emulation environment as well, so you can actually test, debug, and test your application on your desktop without even having an embedded device. Of course, the emulation only goes so far. You can't emulate all peripherals, that are available. So we have some simplistic peripherals that you can use to do emulation, but all the APIs and of course the Java language works as expected. So it's good. The emulation is good to get started quickly, and then you can move to your actual device. And you can do full on-device debugging, source level debugging. Like you would, it's absolutely essential for us as Java developers that you can set a breakpoint somewhere, you can step through the code. Well, for embedded developers, that's like heaven, right? That's really, really hard to do. You have cross-compilation onto some small target that might not even support, debugging, and it just works. I can show you later. I'll set a breakpoint here on the Cortex-M, and it just, single steps through the Java code, and it just works. What type of platforms are we supporting? So that's what I mentioned. So we support this emulation environment for Windows. That's available today. You can download it for free on OTN if you just search for Java Me Embedded. We have our first reference binary is for the ARM Cortex M3, M4. So this is this KEIL board here. I'll show you more in a second. That'll be available soon. We ran into some last-minute red tape, so we're getting that done and putting that out on OTN as well, so you can get started. And then there are a number of other platforms that I'll also discuss on the next couple of slides. So this is the platform. I don't know if anybody attended Steve Chin's talk before. He had one of those. So this is based around the Cortex M3. So that's, if you're not familiar with ARM Cortex, it's ARM's 32-bit microcontroller series that they came up with. It has an ARM Thumb 2 instruction set. it's very limited in terms of its processing capabilities, right? Because it's really about cost and size. But it's still powerful enough to execute Java just fine. There's enough performance. And it's all integrated onto that single chip. So the entire system is, it's one of these smaller rectangular little SoCs up there. The board itself is much larger than what you wouldn't want to deploy this in a real environment, because this is a development board, so it breaks out all the I/O that's on the chip is broken out here. So you can develop your application and use whatever I/O you need, and then typically once you go into deployment, you would have a company build you a dedicated piece of hardware with your chip on it and only the I/O that you need. And again, because it's Java, you'll just drop the jar file on there and it'll just run. So this is a fairly expensive developer board. It costs about $350 US, but it's sort of a reference device. So we chose that to begin with. We support a number of the I/O, not everything on there. We support networking, the SD card with a file system. We can talk on the serial bus, and we can use I/O that's on the SPI bus, I2C bus, GPIO, things like that. So some of the buttons that are on here, the LEDs, the joystick, and a number of things that are on here you can access from Java with this release already. And in the next release, we'll support even more peripherals. So that is sort of the professional version of the developer platform. We're working, one of our partners is Cinterion. I think you've heard, if you attended the opening keynote, you will have heard Axel Hensman from Gemalto. They are implementing or have been shipping their systems for a number of years. Actually, I think Steve forgot his Cinterion module here. I'll bring it back to him. So this is one of these guys, very small. Think of this as a complete mobile device, mobile phone, without a keyboard and a display. So it has an ARM 11 CPU, 500 megahertz, well, depending on the version you're getting. ARM 11, 500 megahertz, 8 megabytes of RAM, different types of I/O, 3G cellular connectivity, runs off a battery for several weeks, and costs about $50 US, 50 to $80 US, depending on the version. So very, very powerful, and it's, again, a general purpose compute platform in a tiny form factor. So it has CPU, RAM, flash, I/O SIM. Cinterion has added a lot of features around remote manageability, connectivity integration, a lot of other features that they've added to our base runtime. And this is being used in a number of industries, be it tracking and logistics. Philips Healthcare built a device for monitoring the breath of patients, and the data gets streamed up to a healthcare provider, and the doctor can actually view all the data online and then actually make changes. So, for example, increase the breathing frequency or the pressure, and that gets pushed down back to the device. So you can improve the care and the service you're providing at much lower cost. So there are many good applications for this. What else did I want to say about Cinterion? Right, and so they're coming out. They've had these modules with Java for about 10 years already, very early adopters, and they're coming out with a new version very shortly that is more powerful, has more features. So that's based on Oracle Java Me Embedded. We're also working with Qualcomm. They have built a universal IoT or M2M platform, which is very configurable and flexible. It has a number of features, and it's pluggable, so you can actually plug in different modules. You can replace different components of the system and optimize it for your particular use case. So it's really meant to get started very easily building sort of advanced IoT type applications. And Qualcomm also partnered with AT&T in the States. They put together a developer program for the Internet of everything. So that's another really good way to get started. I'll talk about the Java Me Embedded 3.3, the next release, shortly. one of the things we're doing with that release is supporting even more platforms. So in addition to these kind of obscure hardware platforms that we have here, we plan to support a very popular small embedded platform that a lot of people are familiar with, and I can't, without giving too much details away, it's named after a dessert with a fruit, and it costs about $35 US. So I think that'll make a lot of people happy, because you can take that device, everybody has it at home by now, and immediately start developing embedded Java. And then you can take, of course that, these devices are way too powerful for the use cases we're targeting, but again, the beauty is you can do your development on those devices, and then you just take your code unmodified and drop it onto a $5 microcontroller, and off you go, right?
So I think the challenge is that the developer goes to that device, and when they want to use that lower end device, then it's a challenge. So do you provide any monitoring tool in your development, SDK, so you can monitor how is runtime, how much memory there is?
Okay, monitoring tools. Yes, very good point. And in fact, we do for the next version, for JavaMe Embedded 3.3 SDK, we will have a network monitor and a memory monitor integrated. So you can, in real time, monitor network traffic and memory usage of your device. Yep, but good question. So let's talk a little bit more about functionality. So, yes?
When you say memory and network monitor, is it a monitor per application you're running on your virtual machine, or is it for the full virtual machine?
So let me think. I believe the memory monitor that we're implementing is a fairly simple but useful way of telling you the free heap per application. So if you run multiple applications, you'll get multiple numbers of the heap size, because you have individual isolated heaps for every application. I believe that's currently the extent, so it's somewhat limited, but still very useful. And actually for follow-on versions of the tools, we're planning much more sophisticated tools, down to things like exact call graph profilers and things like that. But of course, there's always a trade-off, right? Because you want to make these tools run on the actual device with the memory limitations, right? So there is a trade-off. You can't just, port a Java SE tool that'll never run on these systems. So, but we're definitely thinking in that direction. So this is kind of an eye chart probably from back there. Let me start at the lowest level. So the hardware, we support, as I said, a number of different peripheral interfaces and bus systems. So you can talk to, for example, in this demo, I have a light sensor and a joystick hanging off the I2C bus. And I'll show you some code on how you can read the data from those devices. You can talk to general purpose I/O, buttons and switches and LEDs, for example. You have the file system access. And actually, I'll talk about the access to peripherals some more later. Then, this device operating system that you actually never really see as a developer. You don't care. You don't need to know. And then on top of that, we have the standard stack of the CLDC virtual machine. So that's for the connected limited device configuration, and IMP-NG, which many might not be familiar. It's the information module profile next generation. So it's kind of like MID-P, if you're familiar with MID-P, but without the graphics. That's essentially what it is. So it's your application environment. We have, as I said, multitasking, on-device debugging, VM configuration. And then you have a bunch of APIs on top. So on the right side, you see all the standard APIs that you're familiar with. So, XML processing, location-based services, messaging, security and trust services, web services, and file I/O. So, considering this is an embedded device with 2 megabytes of memory, you actually get a lot of functionality. that you do not have to integrate yourself, right? It just works out of the box. On the left, there are some additional APIs, some of which we actually plan to standardize. There are no JSRs for these yet, so we had to come up with our own, and we plan to standardize some of these. So the device access API is the one that allows you to talk to the peripherals. We have a logging API that provides a subset of Java SE logging. Access point API allows you to select between multiple access points in your communication stack. And then what's interesting is the one on the left here, AMS API. AMS stands for Application Management System API. So that is a complete API that you can use to control the behavior of the system. So the AMS API gives you methods to download, install, remove, update, start, stop, pause, kill applications, right? So you can really manage the entire system that way. Of course, subject to permissions. So typically the way this would be used is that you build a system controller application that manages the way applications get provisioned to your system and the way they're run. And that management application would use the AMS API to control the applications, right? Because it's very specific to your use case. But this is something you do not get in Java SE out of the box, right? The Java SE does not have an application model. You have a main method, and you have to put some application system on top, like Java EE containers or OSGI or something. But for these platforms, because we're so limited with the space and we want to provide that functionality, we have something that's built in that works out of the box. Yes?
So the remote application update happens through which API?
Application updates happen through the AMS API as well. So literally the way it works is your system controller application would get a command, for example, from your provisioning server, depending on your specific protocol, saying, oh, here's a new version of application X. And then you would call the AMS API to update that application, and the AMS API knows how to fetch it from the server and then basically validates and replaces the jar file on the system, and then you can start it again. So one of the main benefits that I actually didn't talk about when I spoke about Cinterion in these little wireless modules, so one of the benefits, the reason why Cinterion originally went with Java is these devices are very tricky in terms of certification, right? Because they have a radio stack and they have native software on them to drive the radio stack. You're subject to certification in different countries, right? And you basically never want to touch the native stack on these devices, because once you touch them, you have to go and recertify your device, which takes 3 to 6 months and costs a lot of money. So what Cinterion did was make the native runtime, the native stack, as small as possible and implement all the other features in Java on top, because you can replace and update the Java portion, the applications, without affecting the native stack. So that immediately shaves 3 to 6 months off your development cycle every time, right? So that in itself is a huge benefit. So go a little bit deeper into the dedicated embedded features that I spoke about. So application management system, we spoke about that. The AMS also features lifecycle notification. So if applications start, stop, die, pause for whatever reason, you can have listeners that get notified that they can do something intelligent. You can have applications start and automatically restart. So you can specify in your JAD file, you can set a property, say this is an auto start application, and if the system, if the application crashes or the system crashes for some reason, the next time it comes up, it auto starts the application. As I said, there's the device access API that gives you access to these peripherals, a logging API, access point, on-device debugging, we spoke about all of that. And we can, the OEM or the system implementer that puts this onto a particular platform like Cinterion or Qualcomm, they can easily extend and specialize the product for specific verticals and use cases. So to give you an idea of the things that you can actually do with this today, just out of the box with using the KEIL board. So we put together a demo from the industrial control space, which is a solar tracking system. And it has a couple of additional benefits over your sort of standard solar tracker that you might find in the industry today. One of them is, of course, because it's controlled by Java applications, you can easily change and update the algorithms by which you control the pan tilt unit. So if you want to optimize your system over time, you can do that. You can run different types of applications. And because we have Java with all its network connectivity, and support for sockets and HTTP and things like that, we also added some remote monitoring and management capability to this demo. So let me walk through. So on the left, you have the pan tilt unit with a solar panel and a light sensor. So you can, rotate the servos to, depending on your algorithm, to get the most light or to turn away from the light or whatever. You have a server controller that's accessed via the serial bus. You have some local way of interacting with the device. So there's buttons and LEDs that allow you to do certain things, and I'll show you how that works. The application is written in Java. It's actually multiple applications running concurrently, doing different parts of the system. And then there are two ways we can remotely interact with it. One is we have actually a Java FX application running on a PC, which allows you to basically remotely control the system. And we also have a little Glassfish instance where the application pumps statistical data every once in a while, and it's stored in a backend system, JavaDB, right? So it's supposed to implement sort of a whole end-to-end scenario in a box. So I'll show you how it works. Finally get away from the slides. Where's my... Oh, there we are. Okay. Okay. So I've had a little bit of flakiness with the hardware. I've dragged this around the world for the last 6 months, and I think it's starting to fail on me. But it should work. So hopefully it's up and running. So the first thing we have here is we have a logging. So actually, because the system is networked, we have a log window. So you basically telnet into the log window. And we have a window for the application management system. So we can bring up, these are some of the application management system commands. So you'll see things like AMS install, AMS remove, AMS run, AMS stop. So that's how, this implementation is basically a reference implementation that just calls the AMS API, right? So it's for developer use. And we have this demo, so I can run, actually. So I've already installed the solar panel system. You can see application 0. I just realized it says vendor, so we need to update the properties to say Oracle. But nevertheless, so we'll do AMS run 0, okay, and the application now starts up, and it's running, doing different things. So I'll show you how it works. So yeah, the server controller is kind of flaky. Sometimes the servos just freak out. But so I'm using the local little joystick here that I'm reading through the device access API. So there's no native code involved. You might not be able to see, there are a couple of LEDs here that blink depending on what the system is doing at that point. And what else is there? So locally, so you can control it locally. And then here's our Java FX application, which is running on my desktop here. So I can connect into it. So there's another application running on the system that manages the communication with the JavaFX application. So this is basically reflecting the state of the system here, right? So this could be a remote sort of monitoring control thing. So we've connected into it, and you can see the device state. So there are angles for the servos, right? So for example, if I change that, then they should be updated at some point. Yep. There's the brightness sensor. So if I cover that guy, it'll change or not. What happened? Ah, yeah, there's, I guess it failed to. Okay, this happens sometimes because there's some flakiness with the connector. So I'll just quickly reset this guy and try it again. Actually, before the conference, I was trying to upgrade this and put it in an industrial box and make it more reliable, but then they sent me the wrong box and it didn't fit, so I couldn't do it. Now let's try this again. So I reset the system, and because it's an auto-started application, it actually should have started running automatically. Right, so it's running. So let's connect into it again. And the servo controller hangs sometimes. It's not the most reliable piece of equipment I've ever seen. So I have to reset that guy. Okay, there we go. So why? Okay. Light sensor not connected. Huh. Strange. Of course, that worked before when I tried it last. Yeah, it's moving, but the light sensor doesn't show a value, which is strange. Oh, well, maybe it'll come back. Okay, so anyway, so you can control the system. For example, you can run different applications depending on your algorithm, right? So, for example, we have different algorithms that implement tracking. For example, track brightest position. You can control the device just as you would with a joystick here. It's shaky. And then one of the interesting aspects is here the integration with the backend. So this is a window into the Glassfish server that's actually running locally here as well. So every 5 seconds, the system pumps over some statistics data, and it just gets collected. So if I change the angle of one of the servos, it should show up here. Right. The brightness is -1 because it has trouble reading the sensor. Well, that's the idea. So you can have a fully operating system that controls local hardware, that does networking in different ways, that interacts with peripherals, full Java runtime, and everything on a microcontroller with. This actually has 2 megabytes of RAM. This platform, and I think we only need 1 megabyte to run the entire runtime and the application. So, let me shut this down here. Oh yeah, just to show you, I wanted to show you this as well. So this application is running, right? So I can install a second application. This is the demo application that I'll do next. Right. Oops. I forgot the path. Right. So what it does here, you can either install applications if you have copied them onto the local flash file system before, onto the SD card, or they can be pulled in over the network via HTTP from a server. And so I installed them from a local app. It's just from the local file system, so it's just a JAD and a JAR file. And now you'll see both of them. One is running and the other one is stopped. I don't want to run the GPIO demo because it actually uses the same buttons and LEDs, so they'll start conflicting. And I'll stop the other guy. Okay. Failed. Oh, because it's number 1. There we go. Okay. We'll come back to that. So that was that, just to give you an idea of what you can do with the system out of the box. Let's talk about some code. Okay, so here's a real simple application that doesn't do a whole lot, but you can see that how to access peripherals. We have different managers for different classes of peripherals, I guess you would call them. So in this case, we have a manager for all the GPIO pins in and outputs of the system, of which there are, I think, like 20 or 30 on this particular SoC. So in this case, we just get the pin that's attached to the LED one, and we get the button or the object that handles the button that's attached to another pin. And then we just add a listener to basically the button input, so that we get called whenever we push the button. And we print a short message, and if it happens to be that button, then we change the value of the LED. Right. So really simple. So let's go to where's NetBeans here? Let's fire up NetBeans. Okay, so NetBeans, just like any other project you're working on, the only difference is that you will have another platform. Yes. Why did you go away? Okay. You will have this additional platform here, CLDC Oracle Java Me platform. So in your project properties, you need to select the appropriate platform. So for some reason, the development team called these IMP-NG phone. That's like the embedded platform. And we realized too late, it was like, you can't call this phone. This is really confusing. It's too late to change. So in the next version of the ME SDK, this will have changed and be reflective of the embedded nature of this. Anyway, it's called IMP-NG phone. That's your platform. And that's the emulation. Okay, so let's look at the code. Here's the GPIO, whoops. Here's the GPIO code. And it's pretty much a standard MID-P application. So it extends midlet if you're familiar with mobile application programming. And it has some definitions. Start app is the lifecycle method. This is called by the system when you type in AMS start. This is called by the system. So we grab these pins. We actually support multiple pins here in this demo. Multiple pins and buttons and LEDs. So we grab the objects and we set the listeners. Pause app and destroy app, again, are lifecycle methods by the IMP-NG specification. So when the system stops you, then destroy app gets called. You clean up the resources, you exit. Pretty straightforward stuff. And then the actual functionality is down here. Value changed. So that's the listener that's called. When you push the button, then we do, we set the LED, right? So pretty straightforward. So if we run this code, so this is the emulation. So it'll compile. Let's move this down here. It's compiling and starting the emulator. Okay, here's the emulator. This is the emulation window, and you can see the application running up here. So this is basically a UI into the application management system. And this is the state of the device. So we're emulating 2 LEDs and 3 buttons here, which happen to correspond to what the board here has. So they're all off at this point, and we can inject some events. So this is basically a simulation of me doing something with the pins. So we have 5 pins here. And if I push this pin now, so that's equivalent to pushing this button, then you can see how the state of the system down here changes, right? And every time I do that, the listener gets printed, right? So, you know, not particularly exciting, but it's just to give you an idea for how it works, how easy it is. So now you've written your first embedded application. And we want to do this on the actual hardware. So let's stop the emulation. And now we need to change the device that we're running on. So even more confusing, this is now called external phone 1. Don't ask me why. Anyway, so that is now when it compiles, when you hit run, it'll deploy the application directly over the network onto the device. So we'll try that. And this time it installs it over the air or over the network. So the application management system pulls it in from this URL, which happens to be a local server. And at some point it should be running. Is it running? Yeah, it's running. So now if I push the button, you can see the LED here blinking, maybe. It's kind of smallish. So the exact same thing. Now let's get even more fancy. You see that I've set a breakpoint up here. So let's run it in debug mode. This is just Java, right? So it should just work. Now, your traditional embedded developer will get sweaty hands because this may or may not work for them, but hopefully for us, it'll just work. So we switch into debug layout. And it's connecting, attaching. This takes a while to set up, but eventually it'll be running. Yep. So now if I push the button, yep. So you can see the green arrow. That means we hit the breakpoint, and I can now single step, and it's live on-device debugging on the system. And like in any other Java application, I can hover over an object, let's say GPIO pin. Right. And you actually get the value of that instance. Right. So it's, again, the idea is it's just Java, and you can use your same skills and your same expertise to write embedded applications. So to get to this point, we actually had to do a lot of work, but luckily you don't. That's the idea. Okay. So, almost done. Whoops. All right. So, that's all good. What's next? There are certainly a bunch of limitations on what we have today. The main limitation really being, if you're familiar with the history of Java EMI, you know that Java EMI has evolved somewhat separately of Java SE, right? So EMI was originally designed for very small, limited devices, and so some of the features that you have in Java SE are missing in Java EMI. Things like Java 5 language support, generics, annotations, certain utilities are missing. And so it's kind of difficult to port code. You have to know specifically what's available on Java ME on the platform. So we want to get rid of that. We want to make Java a uniform platform that works the same everywhere. And so you as a developer, you don't have to know special skills. You don't have to know special properties of the platform you're targeting. And in fact, the idea is that you can decide late in your development cycle which platform you actually want to target, right, depending on your needs. So you start your application development, you develop your app, and then at some point down the road you say, okay, now I need to go for a small device or for a larger device, and I'll pick my VM, but the idea is that you don't have to change your code anymore, or you only change it. You of course have to be aware of the resource limitations of the device, right? You can't allocate a gigabyte of memory on a microcontroller, and you can't crunch numbers and start hundreds of threads. But other than that, the code in the application should work the same way. So we want to modernize the platform and standardize some of the APIs so that you have a reliable platform to program to. We filed 2 new JSRs, which is actually, these are the first brand new Java ME JSRs in many years. JSR 360 is CLDC 8. So that's the base platform. That's going to align the VM and the APIs and the libraries with a lot of the Java SE8 features. So you'll have generics, you can use the latest Java SE tools, the system can digest the latest class file versions. You'll have a bunch of the Java SE APIs, including a subset of new I/O and other things. So this is a major step forward, and now, with that, Java ME will look a lot more like Java SE. And then we're putting a new application environment on top. Actually, it's not new, it's an evolution of what we have today. The Java ME embedded profile, JSR 361, which will be much more capable, which will for the first time define things like a system-wide event model, inter-process communication. You have a sort of a service component concept on the system. You have a bunch of new libraries. You have a lot of optionality, so you can target to your specific use case if you need to make a footprint functionality trade-off. So a lot of features. We have this peripheral I/O, which is the successor to the device access API that I mentioned. The peripheral I/O will have many more features to talk to different peripherals, and we also plan to make that available for Java SE. So it'll be a common Java SE ME API, which makes life for Java SE developers a lot easier than what it is today. Let's see, yeah, and so the target markets and the target devices are really still the same, small embedded across a wide range of use cases, a horizontal platform that allow you to really address a wide range of use cases and vertical markets. So if you look at a stack diagram, it's kind of what it going, so it's nothing, we're not fundamentally changing the architecture, but we're ramping and increasing the features and the functionality of a lot of these components quite dramatically. So it'll be a really modern application environment that has everything you expect, but it will still run on microcontrollers. So good stuff coming. This is the roadmap. So we are about here. So I spoke about Java ME Embedded 3.3. That is planned for release in Q1, so very soon. So we'll add additional platforms. We'll implement this new peripheral I/O API that allows you to access more of the peripherals. We'll add some features and usability enhancements to the tool set, to the Java ME SDK 3.3. Then planned for second half of next year is the Java ME8 platform that I just mentioned, so that major update and alignment with Java SE. The Java ME SDK, the tools will follow along with that. In parallel, of course, Java SE Embedded is evolving as well. So in case you're not sure about the distinction, right, so there's Java SE, sort of the standard platform for the desktop, right, which we're all familiar with. Java SE Embedded is the same functionality built on the same stack, but optimized for embedded use. So you can get it for other processors like ARM, for other operating systems. The footprint and performance has been optimized. But for all intents and purposes, it looks and feels like Java SE on the desktop, right? So that's evolving in parallel along the way, together with Java Embedded Suite that I mentioned, that gateway type product. And then along with Java SE 9, you might have heard Mark Reinhold speak yesterday to the future of Java SE platform. So one of the plans is to start tracking ME and SE at the same time. So have the releases aligned. If new features become available on one platform, they will be on the other. So again, the idea being that it looks much more like one platform, and it's easier for everyone. It's easier for developers, and it's easier for Oracle because you only have to support 2 runtimes rather than a bunch, right? So Resources, actually the latest Java magazine that just came out a week ago is dedicated to embedded. So there are a number of stories and articles around embedded, including a lengthy article with me on embedded. So if you want to have sort of broad coverage of what's happening in the embedded space, then subscribe to Java magazine. It's free, but you do have to subscribe. And then if you want to find out more, sort of the intro page on OTN is up here, or if you just search for Oracle Embedded Java. And then the Oracle Java Me embedded page is a little hard to find. You have to look for Java Me on the left-hand side, or you can just search for it. We have the Java embedded community. It's up there. It's actually a redirect onto java.net. And then my blog, where I haven't been blogging as much as I want to, but I try to keep up with the latest in this space. So that pretty much wraps it up. You can start with the Java Me SDK today, right? So you can download the ME SDK 3.2 today. It comes with the emulation environment pre-integrated, so you can start with the emulation right away. And all the documentation is there. There's nice frequently asked questions. There are Java docs. And then very soon we'll come out with these with support for the various hardware platforms. So you can get started right away. And so that's it. Thanks for bearing with me for 1.5 hours in the last talk of the conference. I hope it was worthwhile.